it turns out that most of the slides are actually just by way of by background. I figured that many people have not seen some of this stuff, so it's going to be about 2/3 or 1/2 to 2/3 of the talk will be just the methodology, and then at the end we'll get into the example of how to use how we would be able to use it in the case of firms. And there's actually one, I think, counterintuitive or surprising thing that we'll learn at the end for those of you who haven't seen some earlier versions where we mentioned. Okay. So let me go back to the slide and say the different fields which use these terms. So reliability is something that you see in operations research, system engineering over in the engineering school. Lifetime analysis, sometimes survival or failure time. This is oftentimes what's discussed in biology and biostats, because they're going to say the application would be something like, there are a bunch of people who are newly diagnosed with some potentially terminal disease, and then how long until they actually either get cured or suffer the consequences of that disease. And it turns out, though, in the pure social sciences, this oftentimes goes under the name duration analysis. And for example, so even since the 1970s, economists have looked at things like there is a distribution of the amount of time unemployed people wait until they find their next job. And so how can you characterize that distribution of time? So some of these will involve lifetimes, but it turns out exactly the same machinery is used for all these things, whether it's people being sick or waiting on unemployment lines or whatever it is. So that's the kind of a heterogeneous background, and these different fields emphasize different things. And I'll mention that as we go through. Okay, so here's just some concrete examples. And by the way, I tried to find ABMs where these things are used in one form or another, and if not used, at least it's relevant. So. Everybody is familiar with the epidemiology ones, the trans-Sims people, the Ep-Sims people, and Epstein. A lot of people have worked on epidemiology models. Now, it turns out that this idea of duration analysis or lifetime analysis can manifest itself in a couple different ways. You could say, well, how long are individual people sick for? Now, this may not be that interesting because in some of the disease models, for example, I'm remembering the first smallpox models that I worked a little bit on back in the early aughts. Those smallpox models just had it in a parameter, like you said, that people were sick for 4.5 days, and that was it. There wasn't much interesting there. But how long the epidemic lasts is a consequence of how the people get sick and under what circumstances do they stay sick, etc. So the epidemic can last something longer or shorter than how the sick people are. So all these applications are going to have this kind of micro-macro distinction here. In the case of epidemiology, oftentimes there is good data. About what is the duration of an epidemic or something, and then I'm going to talk only briefly because this is not so important I think for what we do here, but there is relevance to. I want to talk about censoring, which is spelled on here with 2 eyes. Censoring refers to there are going to be some times when, certainly in reality, there are going to be data that presumably fall into this category of being they have some duration, but there's some reason why we actually don't have good data about them. Or, for example, one thing is, it might be that we're running some kind of study, and that we just simply can't run the study until all people in the study experience or succumb to the duration of question. For example, maybe a labor economist is studying unemployed people, and there's a lot of them, there's maybe several thousand, and maybe that even at the end of his or her study, they have not all found jobs yet. So you don't really understand how what is it tell. We'll see some examples of that as you go through. But just to give you some further examples here, so individual people stay unemployed for a certain amount of time. A recession. Now, recessions are normally described by pecuniary variables, not by this unemployment. But you would say that there can be long durations to there can be unusual behavior in unemployment variables. For example, some of you will know that in the last financial crisis, people typically had a much longer duration of unemployment than had been experienced in previous recessions. And typically in unemployment, we instead of having all the data, we have some kind of sampler survey. I put this one down here just because there is that recent book. Some of you may know the recent book by Laver and Sargenti, where they talk about voters being aligned with parties. And then the question is, how long do parties are constantly shifting though, and trying to get more voters. And then as they shift though, they lose other voters. And so people will stay in voting blocks only for a finite amount of time. You can understand it using the same ideas. Some of you know about the model that we built many years ago about housing bubbles. And in housing bubbles, every homeowner who has a mortgage only has that mortgage for a finite amount of time. Then they move and the mortgage goes away. They quit paying the mortgage, and the mortgage gets in some kind of trouble, or they could also be the case that the mortgage just gets paid off, and so mortgages have a natural lifetime. Individual mortgages have a natural lifetime. Overall, a bank holds a portfolio of mortgages, and that portfolio has what's called a term structure, right? How many mortgages will expire this year? How many next year, et cetera. So we can think about those kinds of things. Then marketing and some of you, I think there was a talk a couple of years ago about Procter and Gamble doing marketing where they're giving free samples to certain kinds of customers, hoping that they will get other people to buy the product. And the claim was that a large fraction of all cash register receipts in America are bought by Procter and Gamble in order to understand who's buying what brands. And you are loyal to certain brands in your life, but eventually you will change, or you'll change your loyalty. How long will you stay with a certain brand? Traffic, we all were, probably half of us were stuck in traffic jams of one form or another today on the way in, and individual delays can last longer or shorter. But now the traffic jam might last a lot longer than the individual delays, right? You're stuck for 15 minutes, but the jam may exist for 2 or 3 hours or something. And then the one I'm going to actually talk about in detail today is going to be, individual people are working at firms, and the firms are going to have a life of their own, and how can we understand those things in just kind of just using these ideas of the lifetime analysis. Now, when we run our models, and many of you have heard some version of this talk before, we're going to end up with something on the order of millions and millions, 6 million firms alive at any one instant in time, and those 6 million firms are going to be constantly turning over, constantly churning. And so when you run the model for a long enough period of time, you're going to really get hundreds of millions of observations here. And with hundreds of millions of observations, you can do decent stats on it, right? So that's so this methodology has a kind of a statistical background, which you'll see in a minute. But what we're going to see, just to give a flavor of some things that are going to be coming forward here, is that when we do have very big samples of data, or in this case of having comprehensive data on every firm in America, we're going to see that some of the traditional statistical things don't make any sense anymore, and so that'll come forward here. Okay, so let's initially, just to make it very concrete, let's think about, there's some entities, and to make it computational, we'll say some entities in our model, and the entities all have lifetimes. So no entity lives forever. Something emerges, something arises, it survives for a while, and eventually it goes away, okay? And I've just drawn some pictures here, just to kind of everybody to give us a sense of what we're talking about concretely. So there's a distribution of lifetimes around 10 plus or minus something, and here there's this kind of skew distribution of lifetimes, right? And so for now, let's talk about this in continuous time, because I'm going to eventually argue that continuous time is not the best way to look at it, because in our discrete model, in our computational model, discrete time is more natural. But this just says, what is the probability that the thing's lifetime is around length t? So it's between t and t plus dt, and so this is just the traditional definition of the probability density function. Okay, so nothing unusual here. And we can also think about it in the cumulative terms. These are just once again mathematical definitions, but we're going to emphasize them a little differently than what's usually done in the probability book. So in cumulative distribution function, we're just going to sum up or integrate all those individual PDF to get the CDF, right? And it turns out that in this area in the formalism of lifetime analysis, survival analysis, it's more conventional to work with this thing, because this thing is going to, instead of going from 0 to 1, it's going to go from now 1 to 0. So in essence, you're going to see things like, I'll have plots coming up here, what it looks like, but in essence we'll have a curve with a finite amount of area under it. So the finite amount of area is relevant to what's in some of the calculations that we're going to do in a minute. Once again, just definitions, right? So because of that, we're differentiate the CDF to get the PDF. You can do that, right? And so keep that in mind. We'll see how that's relevant in a second. By the way, if I start going too fast through the mathematics, the notation, just holler. So one thing we're going to compute today, we're going to find an interesting result about is going to be the average lifetime. And so we're going to do it in a completely standard way. And so we just this is just you take the PDF and you put the independent variable there, integrate over the whole range. Maybe it's a little bit less well understood, or maybe this is for people in survival analysis. They like doing it this other way, because f is related to s prime. Differentiate this thing, and you get minus that, right? Just a substitute, integrate this thing by parts, and it's not always, I think, until I've always seen this formula laying around, never paid much attention to it, but this is actually very useful. That the area under the survival curve basically is a measure of the mean. So that the more that survival curve stretches out to time, the bigger the mean, and you can, and the variance has a similar interpretation. But I won't spend much time on that. Okay. This is an idea that is, I think, somewhat unique to this area of lifetime analysis. I mean, we find this idea of hazard or failure rate. So the rate is going to be, we're saying, given that the entity in question, the epidemic, the unemployment, the firm, has survived to time t, what's the chance that it survives to time t plus dt? So this is commonly called the hazard rate, also failure rate. But one way to think about this just says, basically in essence, some firms are going to fail, or some things are going to fail momentarily, but they're not. But we don't want to compute that over all possible entities, only the ones that are still alive. Okay, so in essence, you're looking only at, for those that are still alive, how many are going to die soon? Now, given the definition of this thing, of f is just going to be minus s prime. So if you differentiate s prime, you could do it symbolically as ds dt. Now, if I have ds here and I have s here, this is, if you remember your kind of freshman calculus, this is the derivative of the log is 1 over s ds. So you can think about this hazard function as this. If we plot this thing in this cumulative, this survival function in logarithmic coordinates, the slope is going to be a measure of the hazard, and we're going to see an example of that here in a minute. Okay, so I'll say it again when we get there. But so survival is telling us how many of the individuals have survived. Plot it in log coordinates and look at the slope. It's going to tell us what the hazard is, how the hazard is changing. Hazard is a measure of, for the things that are functioning in our model right now, how many of them they're all vulnerable to dying. How many of them are actually going to die in the next increment of time? This idea is less useful, but it's commonly discussed, so I just put it here. If you just say, well, if every individual is exposed to the hazard right now, and then another hazard tomorrow, another hazard next day, let's just add up all those hazards, accumulate those hazards. So it's called the cumulative hazard function. Now, from the previous result, this equals this thing, and then because this is a pure derivative here, hazard function is just log of the survival function minus. That's not obvious what that means, but that's what it is. Okay, and then if you just invert it, you could rewrite. You could say if I had the cumulative hazard function, I could figure out what is the survival function. This just goes from 1 to 0. Any positive thing here is going to go from 1 to 0. So just some formalism, but it's a way to interrelate these things. So the main things that we had, the density function, the cumulative, and the hazard function, a cumulative hazard, and then then once again, the kind of branching off and just you look at the pure mathematics of the thing. The final kind of conceptual category is this thing, which is very similar to what we did earlier with the moments. But here's what I want to compute now. I want to say, given that the entities have survived until time t, let's compute the life expectancy going forward. So now, this is not the life expectancy of the whole population, because we're saying let's only pick the ones that have survived until time t. What is time t? Well, it's just a symbol here. So the beauty of this calculation is that it's going to do it for all t. I can do it for any t, right? So here's one way to think about it. So imagine I have some survival curve. We're going from 1 at time 0, where they're all surviving, to some point in the future where they're not all surviving. What we really want to compute, what this really computes is it says, okay, given that I'm at some point in down survival curve, some of the individuals have already passed away, or they're already gone. What is basically the life expectancy of those who have survived until now? Now, some of them are going to die in the next increment, but some are going to last for a much longer time. So in essence, you can think this is in this calculation, the life expectancy is going to rise, right? Or it's because over time, because you're basically the ones who are most likely to die are the ones who have died already. Okay, so it turns out one thing you can if you can integrate this thing by parts. and using the same ideas as before, that's going to vanish, and so you're left with this thing. Once again, the area under the curve is going to be a measure of this, but now notice that because it's all parameterized by t, if we put in t equals 0, we just get out the mean value. Okay, so the residual life expectancy from at time 0 is going to be just is that t bar. But and this goes by various names in various different communities, and I'm not going to go through many of them. But for example, but just as an example, so in engineering and operations research, this would be called something like the mean residual lifetime of the machine in question. In demography, this is oftentimes goes by the name force of mortality. That is, what's the the force of mortality can be used to compute how much remaining lifetime the individual people have in the society, etc. Now, just to build up our intuition for what this means is think about the way it works for human societies. Now, I'm going to eventually get to the point where we're going to say there are a lot of populations we care about in our computation models that look a lot unlike human models. But and we know what this means because there are very few humans that live to say age 100 or beyond, right? So the average life expectancy is something like so t bar for humans would be something maybe like into the 70s and 80s, right? Upper 70s probably for men and lower 80s for women. I don't know what the current numbers are. But you think that as you there's a little bit of at childbirth there's a little bit of higher mortality for the infant mortality and things. But once you made it through that, then as you get as you become age 30, age 35, age 40, right? As you make it through those windows of time, your average remaining lifetime is increasing, right? And so you can think that once you made it through age 80, you have a chance to make it to age 90. But if you can't make it to age 80, then you're not going to get to age 90, right? So this is a measure of you think about it as being life expectancy, but it's life expectancy contingent on having made it to a certain age already. Now, in the case of humans, the way it basically works is our hazard, or the failure rate basically starts going up very dramatically as we get into our 80s and 90s. We're going to basically have, starting to have very large probabilities of annual failure, like 10%, 15, 20% chance of not making it for the next year, right? So that's why you see no individuals who are 150 years old. I recently saw that there was the oldest person recently was
Janine Clement. The French woman, Janine.
Yes, exactly.
Yeah.
And then it was believed that she may not be that old. That someone said that there was one demographer thought that it's possible anyway that she had actually taken on the persona of her mother.
Right.
And it added 20 years to her age. She was really 20 years.
Still, she was either 130 or 110.
Exactly right. But I think there was some crisis during one of the world wars when her mother died, and she may have taken over her mother. Okay. So here's a concrete example, and this is the marginal case. So it's useful to just go through in detail. And I apologize for the kind of undergraduate class of mathematics here, but we'll go through it. And so this exponential distribution, which I did not draw a picture of, but everybody knows what it looks like, right? It's just declining, monotonically declining, and it has this PDF, which gives the average lifetime is just going to be p. Okay, when it's written with the p in the denominator here, think about this. The p just normalizes the time. So whatever the p is as a normalizing factor, that makes the average lifetime. So let's say it's for a human. Let's say the average life expectancy is 80. This is not applicable to humans, by the way. But if it was, you would have p would be 80, and then you would have this appropriately declining function. Here's the cumulative distribution function. 1 minus that is a survival function. Now everybody knows what that is. That's just monotonically decreasing. Right? It starts out at 1, right? Put in times 0, you get 1, and as time goes on, it goes to 0. No one lives forever. The hazard rate is just going to be that divided by that. Notice that the exponential term is going to go away, right? So you're going to end up with that. So basically, 1 over p is going to be the chance of failing. So imagine it's 80. So imagine if the average lifetime is 80. Well, then 1 over p is going to be, you have 1/80th chance of not making it until the next period. Okay, this is continuous time; it's not discrete. But so look at the cumulative hazard. So if you face a 1 over p every period, integrate that over time, right? Over time you face a bigger and bigger hazard. That's all we're saying. That's all the cumulative is, right? Just more and more hazard. and then this remaining lifetime, maybe I should comment on this. How does the hazard depend on time? It doesn't. It's just a constant. And so this is this marginal case. Whereas, and what is the average lifetime? This is the average remaining lifetime, and that's also just a constant. So this is the case where the simple case where nothing depends on time. The more interesting case, and the one that we'll actually be using today when we get to the firm's data, is this one. So this is the Weibull distribution in continuous time. I'll mention how in discrete time it's a little bit different in a minute. With two parameters, the Q parameter, because it's the exponent there, is a shape parameter, and P is once again kind of this normalizing parameter. See the average depends in this non-trivial way on both P and Q, but it's linearly proportional to P. So basically, P once again P normalizes the time. Now, if you look at that functional form, if Q is 1, that's just unity. That drops out altogether, and then we just recover the exponential. Okay, so the Q equals 1 case is the marginal case, and it's very common to have both Q bigger and less than 1 in various facets of the way these models are used in science. Let's just look for a second at think about conceptually at the Q less than 1 case. So if it's Q is less than 1, that's the case we're going to find empirically in a little bit. If Q is less than 1, in essence, this term is kind of we're kind of stretching time, warping time a little bit, such that if when we compute, here's the cumulative, here's the 1 minus the cumulative, so the survival. And so when we get to the hazard, what we see here is that if Q is less than 1, remember the hazard was just going to be this thing divided by this thing. So the exponential terms decay. So it's just, the hazard is just that part. So, but if Q is less than 1, then this exponent is negative. Okay? So the exponent is negative. It basically says as time goes up, this goes down. Okay? And then the exponential case is Q is 1. Well, Q1, right, that drops all the other, and that's why you get a constant there. Q is 1. If in fact Q is bigger than 1, then you're going to see the hazard is going to increase. Or then as T gets bigger, H goes up more quickly than T. Or H just goes up. Okay, so the Q equals 1 case is the marginal case. But I want to focus once again on the Q less than 1 case, just to say that what does it mean to have the hazard? Let's see, Q is less than 1. As time goes on, hazard falls. It means that as time goes on, there's less and less chance of dying. That may seem very counterintuitive from a biological point of view, right? It's kind of a sultry intuition because in real human societies, basically as you age, certainly at the end of human life, Q is much bigger than 1. So are there really systems where Q is less than 1? So just think about that for now. I'll come back to it in a minute with an example. Okay. All right. By the way, if anybody wants I'll send you the slide deck if you want it. I did put the basic results all in like a 3-page paper. So if anyone wants the paper, send it to me. But this just says if you know any one of these things, you can compute the other one. Okay. So in some sense, it doesn't really matter which one of these things you start with. You can get the other ones. They're all it's all just part of the same system of relationships. But you're going to see in a second where, based on having empirical data, it may be useful to focus on one or another or a different one of these things. But the main thing to say is that if we have data and can estimate one of these functions, we can get any of the other ones just by explicit computation. Okay. I mentioned that for our computational models, it's almost always easier to do things in discrete time. Why? Because we're time stepping somehow, right? We're taking individual actions. So this is just kind of repeating the same formulas from now without going into all the details. Just showing it in discrete time. In discrete time, you're saying like there's going to be some action at time 1, at time 2, at time 3. I've written here. This is just imagine this is a geometric distribution now. The geometric one is the discrete analog of the exponential, right? And so we see that there are very few entities around with lifetime 20. The average would be in here somewhere 5 or 6 or something. So once again, you have the probability. Here's the cumulative, just by summing up the individual probabilities. 1 minus that is going to be, I just changed the index from less than to greater than to get the survival function. We can compute the expectation in the usual way. You can actually do some, if you've ever seen this before, you can do summation by parts instead of integration by parts, right? You can get average that way. Hazard function defined in more or less the same way. It's slightly different with the indices here, but this just says this is how many individuals have died in their lifetime is in fact T sub I. This is how many people started the previous period alive, how many individuals started alive. So basically the fraction who died over the fraction who were alive, that's a gross estimate of the hazard function. And there are other ways to estimate the hazard function, and I'll talk more about this in a second. So maybe I'll just interpret it right now. The survival at time Ti basically is, the H's are the ones who have, this is the kind of the fraction that have passed away. So if you subtract 1 from the fraction who have passed away, this is how many have survived that period. So if you just take the product, or you say, right, a certain fraction survived, and then another fraction survived, another fraction survived. I don't know how many survived through age 10. I just keep multiplying by what fractions have survived, and you get the actual survival function. Okay, so here's the simplest example in the case of discrete time. The geometric distribution once again be discrete exponential. So the PMF is just that thing. There's some probability of failure, be anything between 0 and 1. The CDF is that. The survival function becomes just 1 minus that. The average is going to be that, and the hazard function now, just the ratio of that to that essentially, comes out like that. Once again, the details don't matter, but this is once again, this is just a case where notice it does not depend on time. This is the boundary case. But what I'm talking about now is that if we have some data, how are we going to estimate this thing? And so it turns out that in the statistical literature, there is this thing called it should be called product, not produce. Product estimated. It goes just like I said before, so you want to basically, you're going to use this product in this way. So it just says there are some, of all the things that are living at time t, some of them are going to die over the next period, and you're going to divide how many died by how many were alive at the start of the period. That's an approximation of what the hazard rate was. So 1 minus hazard rate is how many who did survive, and so you keep multiplying over the different periods how many, like this other type, that should be T sub j, because it's the index j, so it goes 1 to I. Right. So this is a measure of, this is an approximation for what the survival function is. Now in the case of having discrete time, I just put in a typical one that I've estimated for a different problem, but you're going to get these kind of step plots here. Now the Kaplan-Meier one technically was introduced. Kaplan-Meier is a slight sophistication I'm going to talk about next. Kaplan-Meier was invented to deal with the problem that we encounter not so much in our computational models, but rather in biostatistics. Imagine in the biology case. Imagine that you have some number of people who did not survive over the course of the next period of time, where they're getting some cancer treatment or something. But the number alive actually has changed, both due to the fact that some have died, but it might be also the case that, for example, maybe 1 or 2 of them got hit by a car, or maybe 1 or 2 of them just moved out of the country or something, or out of state. So you want to be able to deal with the fact that some of the data may not be present, and so that's what's called censoring. And so in censoring, we're going to say that for some reason, it's just the case that we can't actually know what is the lifetime of everything in our sample. Now, as a practical matter, one reason why you're not going to know the lifetime of everything in your model is you actually turn the model off at some point. You turn the model off when there were still things alive in your model. So on those entities that were alive, you actually never got data on how long they lived. So you just want to. So the idea is just take the number that died in this case of lifetime idea, but divide by not just the number alive, but the number alive, but subtract out those who exited for whatever reason. And for example, so the case of just think about the case of our mortgages, and we dealt with this a little bit in our mortgage model that we built many years ago. That we wanted to figure out, what was the hazard rate of people defaulting on their mortgages, and you had to be careful that you accounted for only those that actually only the mortgages that quit being serviced, people quit paying on. Not for example, the mortgages that died due to the fact that somebody moved out of state or something. So this idea of censoring, now there is a lot more to be said about it. I'm going to argue just in a minute, though, that it's not that important, and I think it comes up in the very next slide. For example, in this biostat literature, there is this concept of Greenwood's formula being the variance around one of these survival curves. So I'm going to go back to 2 slides to show that survival curve. And this is the point estimate of some survival curve. And what you want to do, particularly with a small sample, you like to put error bars around here. Like, what is the possible range? Is the range going to be very tight here, or is the range going to be quite large? Right? So this Greenwood's formula is a way to estimate the variance around the estimate of the around the point estimate of the survival function. Okay, but now look at that denominator. It's got n in it twice, and where n is the number of samples. Okay. Now imagine that we, in one of our computational models, we have some fairly large amount of samples, or some large amount of entities, and it appears twice here. So that's going to mean that basically you've in fact shrunk those error bars down so far that essentially they're non-existent. So I'm going to show you in a little bit that when we talk about the data we have on firms, that this doesn't really make any sense for our models because the n is so large that it basically says that the data are there. There's no error on the estimation process. Okay, so what I want to go on to now is just a slight sophistication, and if this is now we'll move away from for example, all the kind of biostat interpretation, a little bit more into the way that I think that we use things in computationally. But so this applies a little bit less to infectious disease, a little bit more to something which has a finite lifetime in one of our models. So think about the fact that the entities in our models will have some age, whether they be people or firms or mortgages or whatever they are. They're all going to have some age. So I've written now, what I try to do here is, this is actually a geometric distribution of things by age. So the red dot refers to the age, okay? So imagine that it's this instant in time, I have 20% of the things are brand new. They were just born. And then 16% of them are age 1, right? And 12% are age 2, etc. So this is the geometric distribution, all the red dots, okay? But if this distribution is stationary, this is not changing over time for some reason. Now, of course, in reality, we don't always know our models dance around a little bit, but imagine this for the purpose of discussion, say it's stationary. Well, notice that the discrepancy between this point and that point, that's a measure of how much death there was. That's a measure of how many. If we have 20% of the population is age 0, but by the time that cohort ages 1 unit, there are only 16% of the population. That means that 4% of the population just vanished. They're gone. And so they have to have some. We're going to say they have some age. Now you can call them age 0 or age 1, just by convention. Here I'm going to call them age 1, and the black dot is a plot of what is the corresponding lifetime distribution implied by the red age distribution. Okay. Now see how to compute that is. If I have 20% here are the youngest cohort, and 16% are the the age 1 cohort, I've lost 4%. Well, I've lost 4% of 20%. And that's 4% of 20% is 1/5. So that's why the black dot is up there. Okay? And then when I go from the age 1 to age 2, I lost another fraction, that fraction, but I didn't lose that fraction of the whole population, I lost that fraction only of that. So that's what that dot ends up there. So basically the black dot is in fact the lifetime distribution that corresponds to the red age distribution in discrete time. Is everybody okay with that? Now, it turns out in this particular case, I've drawn this as geometric, and so when you do it as geometric, it turns out everything is just displaced by 1, and so it turns out the age distribution is just left shifted once from the lifetime one. But that's not essential, and we're going to look at empirical data in a second to expand that. Okay. So now, to get into the concrete example, think about firms. Okay. And think about having data on firms, and you now have a model of firms. Okay, so entrants are the firms that have just come into the economy in 2019. They're coming in right now. We don't have fine-grained data. We don't know how many. We have estimates of how many come in every month, but we know exactly how many come in over the course of a year because they file tax returns. Okay, entrants. These are the ones that have made it through the first year and are age 1, but some have exited. All the ones that did not all the ones that started up in February of 2019. And did not survive until December 31st. They're the ones who dropped out. We're gonna call them the exiters at age 1. Okay, we don't know when they maybe they only exited, maybe they only were in operation for a day. We don't know, but we'll call them that for 1. So I've drawn the boxes here to be. So we have monotonically shrinking number of firms of each age, right? Because we keep dropping out more and more of them, and then time is marching on until we have some oldest set and. Now here's where censoring does matter in the case of these data is that we all know that there are old firms in the economy. IBM is an old firm, Standard Oil of New Jersey, Exxon. Esso used to be, right?
Yep.
It turns out that the U.S. data that are available really only go back to, we have estimates of age only back to 1975, okay? So really we have something on the 76. So we have on the order of 45 years worth of data. And for firms that are beyond that, we don't know how old they are. But I'm going to show you so in essence, those are censored data. But with 45 years worth of data, we can estimate what is the functional form governing that age distribution, and then extrapolate, and we'll see what that tells us. Okay, so this is the basic conceptual point of view. What I'm going to show you next are data. Okay, so the different color lines refer to 5 years of data from 2002 through 2006, and basically every line says, okay, imagine we have the year 2002. These are the firms that were born in 2002, 2001, 2000, 1999. So this is age, how old the firms were that were around in 2002. Okay, that line is one of the color lines. I forget what the color scheme is, and then we superimpose that with all the way up through 2006. Now, I think the first thing to say about this, notice that we're in logarithmic coordinates here. A little bit hard to see it. This is linear this way, log this way. Okay, and so those continuous lines are the data. So the first thing I want to say is that these data are mostly stationary. That it's not changing with time, right? So basically, we have even though the number is going to change a little bit, the numbers will fluctuate. When it comes to the distribution, that's not changing. And look what it says here. About 10% of the newest firms, about 10% of all firms every year are the newest ones, are the babies, are the entrants. Okay, keep that in mind. Keep the 10% in mind. I'm going to show you something a little bit different in a second. Now the dots through here are at discrete times, and of course we only have the data in discrete times. So this is basically a fit of this discrete. This is a discrete version of that Weibull distribution I showed you earlier, right? It's kind of, we normalize it and we put it to a power in order to make it work out right. This is one among other. There are several different forms of the discrete Weibull. This is one of them. And for certain values of P and Q, we get those black dots. So the black dots are pretty good fits through the heart of that distribution, or through the heart of those data. Everybody okay with that? Yes, Dick.
How do you define death?
So here, basically, it's because these data are based on IRS tax returns. Firm quits using the same tax number on its.
Okay.
So it's used over 5 years. It's used this tax number. That tax number receives no return next year.
If it got bought out by another company and continued in operation, by your definition, it's dead.
Yeah, and technically the way the census does a little bit better job on it. So what census does is they actually put those assets into the tax number of the new firm, so they actually know that they know that. Here the term of art is the enterprise is the company, the establishment is a local operation, and so they actually will wrap the establishment into the other enterprise. So.
Okay. And when you have a company that's basically been limping along in Chapter 11 for 10 years, by your definition, it's still alive.
As long as it has a tax return, it is.
Yeah.
Okay. May not be profitable, but it's alive. Okay, so I want everybody to remember this one number here. The average age of American firms is 14 years. Okay, so average. Now this is a skew distribution, obviously. So we're going to have the case where the average will be a little bigger than basically the mean is bigger than the median, which is closer to 7 or 8 years, and of course that's bigger than the mode. The mode is going to be 1 0 1 year. Or the most common size firm is 0 1 because from that you winnow down into smaller into fewer and fewer firms. Okay. Now I'm not going to talk much in this. I'm not going to. There is a whole. We've done a bunch of work. Joe Sheen did a bunch of work in his dissertation on what was the effect of the crisis on this thing, and basically the financial crisis of 2008. It's really 7, 8, 9 corrupts this thing. I'm going to show one slide about that, and that's it. But we can talk more about that at the end. So remember this is 10% of all firms are startups. So this is now plotted Roy G. Biv, 9 through 15. Okay, and it goes 9, 10, 11, 12, 13, 14. And what you see here is that notice you're down to 8% of new firms are startups. So there's a gap. This immediate gap. We've had a dramatic fall off in startups. Now you see it's gone from 10% to 8%. that's a very small number, isn't it? There are 500,000 new firms a year. So by having that fall, you're basically losing 100,000 new firms are not there that were there every year. That's a giant fall off. I mean, this is logarithmic coordinates. And then what you see basically, that depression there gets, those firms that are here are now the age 1 ones when it's orange, and the age 2 ones when it's yellow, and the age 3 ones when it's, you can see this thing going up here. So basically this imperfection that has been impressed into the early stages of the age distribution plot are basically, this is going to propagate. This is going to propagate all the way down. So when one of your students is looking at this data 30 years from now, okay, you're going to, this whole thing will have shifted. And it's shifting, and there's a new distribution taking shape, right? Here you can see the new distribution coming here, and it's going to be different than this. So the main thing to say is that since 2009, this thing is certainly not stationary anymore. It's got this defect in it, okay? And we have to give it a fun name. If you have any thoughts about that, we have to figure out what to call it. Natural scientists are wont to say that social scientists can't ever predict anything. Yeah. We predict in 15 years that we'll see this thing down here. This is just the snake eating the rat. Did I say that right? Yeah,
Is that the anti-bubble?
Yeah, right. Yeah, the depression. This is a very slow-moving system. This is the giant battleship that takes 30 years to turn. It's got that thing it's got a pattern in it which is going to take 30 years to play out. Okay. From those data on ages now, we said that if the ages are stationary, so we're going to look now, this is only for the 2000, this is the pre-crisis data. The ages imply lifetimes. And this ugly thing here is what the survival function is for that discrete Weibull. And you see the different curves. Now, they're a little bit messier here, especially in this range. And then the dots are a fit of this thing with, P is about 12 to 13, and Q is, I should have said that before. Q is this number. Remember, Q is decisive whether Q bigger or less than 1. Q is about 0.8 in these data. So Q is 0.8, and it does a pretty good job fitting the data though all the way down. Okay. Now, once we don't know what happens out here, so we can extrapolate and say maybe the Weibull fits those older firms too. So here's the survival for the post-crisis data, and it's all messy. I'm not going to mess around with that. Hazard probability. Okay, now we have this analytical expression for the hazard here, and so hazard is a chance of dying. I've called it exit just because the word hazard is not used by economists. So, but exit is, and this plot. This is just two ways of showing the same data. This plot though just confirms the intuition that basically young firms have a 25% chance of failure, but as that declines quite rapidly. And then by the time you get to be age 20 or so, you're down into having only a 5% chance of failure. So this is the idea that there's some risk of being simply young, right? The risk of risk associated with youth. And now in that plot I've just taken. So this is a linear plot, linear. This is now. I guess this is going to be log. It's certainly log that way. I guess it's log that way too. So it's log, and it's not obvious with all these nested exponentials that this will be a power law, but notice it does. It's kind of straight. It's almost a straight line in this log space. Not quite. But what's very clear from this is that as firms get older, they have a much lower probability of failure. Now, in order to understand what that means conceptually, I like to use the following example. Imagine that I'm standing here next to my son and my father. Okay. And we're all standing at the same position in the year 2019. If humans were like firms, we'd have the following very weird forecast. It would be that my father would live longer than I will live. He'll be on the planet longer than I will be, and I will dramatically outlive my son. Mm-hmm. So that's the sense in which this is very, very non-biological. Well, I used to say it's non-biological. Now, Joe Shaheen in his dissertation, he actually discovered that there is a wide class of biological populations that actually have this feature. And think about it for now. I'll connect it at the end. Okay. But the main thing to say is that a firm, right? The risk of exiting falls sizably. Remember, it's exponential coordinates. Log coordinates fall sizably with age. But that's only part of the story, and when I get into now an important other thing, well, maybe this is just a different way to say the same thing. Now, if we can compute now, given the fact that we're in this world of having declining hazards, we can compute what is the average remaining life, what is the expected remaining lifetime of American firms. Once again, a little bit messy formulation here, but what it says basically, if in fact the firms are age 0, right, so the expected lifetime is right around here, or the expected lifetime actually is here, so it's right around 10, I don't see the dot, but it's right around 10. But as if you can reach age 20, you have 20 years to live. If you reach age 50, you have 25 more to live. If you can reach age 100, you have another 28 years to live or something. So you have this increasing lifetime, and this is the kind of the part of it that assaults your intuition. Now, I did actually remember a while back what the average age was. And the average age is about 14. The average lifetime is 10. How can that be? Once again, it assaults your intuition for aging, right? It's a population of entities for which the average age exceeds the average lifetime. But it's precisely for the reason that we saw in the previous slide, right? It's precisely that you have this giant infant mortality here.
Yeah.
There's so much die-off from the young ones that you're in this strange world of but it's not a world that we're very familiar with in our we're thinking about our your siblings or your parents or something. See, but this is not the whole story, because what we can now do, and this is now something which there is good formalism in this literature, which I'm skipping just for in the interest of time, but it's if you want to know more about it, I wrote it out on these few sheets of paper that I did. Happy to send you. Here we compute what is the exit probability. Well, we're now going to disaggregate the whole population into whether it's a small firm, or small firm, kind of a bigger firm, medium firm, or a large firm. Now here's the rough, I've not said much about firm size here. Half of American workers work in firms that are 500 or bigger. But only a small fraction of firms are 500 or bigger, right? Something on the order of a few percent of firms are 500 or bigger. But half of American workers work in here. Almost all firms are this size. Okay. In fact, the median firm size is 4, so about half of all firms would follow the red line. So what we had before was, as firms simply get older, their chances of failing go down. By the way, I want to actually calibrate on the numbers here. So this falls down to around 0.05 here, right? So you think as you get quite old, your chance of failure is 5% per year. But what this is telling us now, but if you look at that's up here. If you're just if you're 10 times the median, you're now way below that. And if you can become one of these biggest firms at 50 years, and you're an order of magnitude even below that, right? So the chance of failing now, this is right, that's 0.5%. That's under 1% per year. Okay, so this would tend to be called a covariate, where we're using size as a basically the parameter of the parameters of this survival function P and Q depend on size, and they do it in the empirical way that I'm showing you here. The functional form is messy and complicated, but it has this effect, and I've summarized it in this way. What is the role of size? What's size doing here? Well, so now let's pick a certain year. Say, let's look at all the firms that are age 5. Well, an age 5 firm, a small firm, has a 10% chance of failure, but a age 5 large firm has a 3% chance of failure. So what size does is somehow it basically slows down time. It slows down the firm's exposure to death. Every period you're getting this risk, you're taking on this risk of dying or passing away, and size is insulating firms against that. Okay.
Are you accounting for firm growth over time, or is there now you're at the...
This is all firms, Karen. So this would be some of these firms are growing, some are shrinking. So growth is another variable to consider. And we could in principle unpack this by here. I've unpacked by one covariate is size, another covariate is growth. We have the data on that. We haven't. This has already been complicated enough to look at this. We haven't done that, but yeah. So
because I'm thinking about as the firm grows in age and grows in
Yeah, that's right.
size,
Yeah.
right? That's the assumption, I guess. I don't know if that's.
So, well, yeah, so for one of these firms that's let's take one of the green firms. So one of these firms that say it's size 100. There are two ways to become size 100. You could have gone from being small to large, or you could have gone from being large to small. Both paths are realizing the data. And Shaheen, in his dissertation, by the way, he shows us what is basically the transition probabilities from the different size classes. So we can compute those things. But we all heard stories about it. Even though size size attenuates the risk of failing. We all heard the stories of for a firm that grew too fast, and then it took on too much debt, or took on shoddy practices, business practices, or something. So size need not be the only factor we consider here. But I guess the main thing to say is that one upshot of this thing is to say that it is the case in the law in our country that we tend to think of firms as being something like people. That is, they have certain kinds of rights, like speech rights, quasi free speech rights. They're able to, these days with Citizens United, they're able to donate to campaigns, that kind of stuff. But remember, the word firm or business or company does not appear in the Constitution. All the rights given to firms were invented by the Supreme Court justices along the way. And this just says, for a firm of this type, this firm is utterly unlike all firms are utterly unlike people, because their risk of dying falls with age. Basically they become hunkered down, they become more fit somehow, ways we don't understand fully. But then a big firm is even more extreme, right? A big firm has, think about it. Imagine we had done this for those of size 5,000 or bigger. That would have been even down here further, right? So you would have had some. There's almost no chance that a size 5,000 might get taken over and have its tax number folded into some other one. But the chance of actually running the business is very small.
What more often happens is that a large line of business collapses, and if you're some medium-sized software firm and your main product stops working, you will probably in one way or another go out of business. If you're IBM and Watson fails completely, you've got 35 other lines of business that will sustain that firm for a long time.
Okay, so this is just meant to be to show kind of these various different functions that we've discussed today. Here we're looking at the ones that are monotonically decreasing, and now plotting them on log coordinates. So here, these are the ages of the firms when it fits this Weibull, and now it gives us this set of lifetimes. So they're similar in character, but not exactly the same. And then that corresponds to this survival function. But then the key, I've argued in understanding, is that this exit probability is declining, and that's giving rise to all these unusual properties. I mean, every real life entity will have a declining age distribution and declining life. This would be typical, but the fact that this thing is declining is given the unusual properties to this set of firms. Okay, so the summary of this talk is basically that these techniques, which I did not know a lot about when we started getting into these data, seem like they're relatively useful for characterizing, understanding, what is when we have heterogeneous entities running around doing various things. We want to characterize how they behave overall. This may be a way to help us understand kind of the transient properties of some of these things. I wrote here that this methodology seems quite relevant to our stuff, and then some of the received wisdom may not be very useful. Error bars are not very useful. One of the things that we seem to do that the bio people seem to struggle with is they often always complain about that the data is not very good. They have a small sample. They have errors in the recording the data. Of course, in our models, we can almost always, we can get exact data on the things that arise in the computational models, right? So, in some sense, maybe one way to deal with censoring is to say, you're worried about the fact that you got to turn your model off. And so you censored the last tranche of things that were rising in your model. Well, next time run it a little bit longer, right? And then you'll fix that problem. You can see what's going to happen. And then I've written here there are further techniques in this. In this stuff that I've skipped here, associated with heterogeneity, and I want to just give a flavor of it. I'm going to go back to the previous plot here and say, think about this thing. Think about the fact that exit probabilities are falling with age. Now, always in our models we have at least two levels. Right? We have the agent level and we have some aggregate level, social level, macro level. Mm-hmm. Now, it's very easy to get involved with fallacies of either composition or division. Right? The classical philosophy 101 fallacies would be, I see something happening at the macroscopic level, And so I assert that must be going at the microscopic level. And to some extent, this is modern macroeconomics, right, with representative agent. And then it's also the case that the fallacy of composition would be to say, I know what's going on at the microscopic level, so I simply assert that well, the macroscopic must be just an n-fold replica of that. Somehow, right? So now, but I want you to think about this now. Imagine I told you. Remember how it was the case that the exponential distribution, having a constant hazard probability, having a constant failure rate, would be a straight line going across here. A constant failure rate was that boundary between things, living longer or having a lower probability of dying or having a higher probability of dying. So imagine it was the case, though, that we said that there's a large population of entities. They all have a fixed population, a fixed probability of dying. But the key, I think, I want to suggest here is that they have a fixed probability of dying, but it's not the same in the population. Okay. So imagine we have a fixed population. Everybody's exponential. So what's going to happen? Well, if we have a heterogeneous set of in essence, death probabilities, what we'll see is the ones with the highest death probability will die earliest.
Yeah.
And then you'd be left with progressively a perverse sample of progressively longer-lived entities. And so you can get this thing happening naturally by just having heterogeneous exponential rates, which is something which the reliability guys stumbled on a long time ago, but which seems to be quite new to interpret in the survival world. So I guess one lesson for that would be if you say, I've got a declining exit probability model here, and it's producing these weird results where the average lifetime is shorter than the average age. Well, it could be because you have this kind of Weibull distribution of failure rates. It could be that the failure rates are actually declining with age. But it could also be the fact that it's simply a heterogeneous population. And as of today, we don't know how to unpack those two. Those are two different explanations for the same thing. And without more data, we would not know how to unpack that. Okay, so I'll stop there and take some questions. Yes, Ken.
So I'm wondering whether this might apply to certain organizations where have been theorized to be technically immortal. Jeffrey West over at SFI talked about cities, and that's his passion project, on how a city, in essence, is immortal, such like Rome never died. It transformed and changed and modified, but it's never died. Whereas firms and other human institutions have died.
Right. Yes.
Is it a matter of
well-defined lifetime?
Is there a matter of that we just don't live on we haven't seen these life scales long enough, or whether it's something where a completely different kind of generative function that we're looking at.
And of course, if you look back over the kinds of historical times that you'll be teaching in the fall, then you will see places like Alexandria kind of come off the map and other kinds of things like that, right? But, but right, on the time scales of kind of at least of the last Western of the post-Renaissance time period, we don't see cities go away, for example. Right?
Exactly. But
a few of them.
You're thinking Detroit, Doug, isn't it?
I'm thinking Warsaw.
Warsaw, Poland.
Yeah.
But it's still a city called Warsaw. I can find it on the map.
It's quite different. It's all around.
In May of 1945, the population of Warsaw was fewer than 1,000 people.
Still greater than
They
zero.
had to rebuild it. It was a laborious process to put a city back there.
Sure. And there were periods in Rome during the Middle Ages where it was less than 1,000.
Yeah.
Still, there was a city of Rome.
Yeah.
So anyway, sorry.
Yeah, and so just as a footnote, you know these data too, but the U.S. government really defines metropolitan and micropolitan areas have to be like 25,000 or more. Right. It'd be interesting to see, what kind of cities, industrial, whatever, are kind of falling below that threshold, kind of coming back and kind of going below. There's the people there, of course, but maybe they're just not doing the same thing they were doing before. So.
Right.
Yes.
Similar to your firm size, is there a difference between sectors? So, for example, from a naive perspective, from someone who doesn't do this sort of research, I would say that it's that the relative probability would be higher for energy rather than tech, for example, right?
More or less, more turnover or less turnover for energy?
So less turnover for tech or for energy. So if you're Exxon, you have a much higher chance of staying in business rather than
Yeah.
Apple, I guess.
So I guess the question is, if you control for size, is that true? Now, so it turns out, yes, so to do sectoral work is important, and the data are roughly available to do it. Here's the trouble with doing sectoral work is that basically we lose sample size.
Yeah.
So we had with 6 million firms, time you get the most crude demarcation of sectors is roughly 40 sectors. And so now you're down to, in some industries you only have like 10,000 firms, and so but I think your point, to me it's interesting because I'm not sure my intuition was the same as yours, having lived in Houston in 1982 when there was a giant fall in the price of oil, is that control for size and there are no high tech firms with the size of Exxon, for example, right?
Right.
So to take firms that are the same size, is there a higher hazard rate? It's my sense is that many of the Bay Area companies get gobbled up by the investors as they either don't make it to market or something, right?
But the energy companies are typically regulated monopolies as opposed to competitive. So it's kind of like zoo animals versus in the wild.
Utilities, at least, because they
Yeah.
Even then, like, no one expected Pan Am to fall apart until it did.
Yeah.
Fairly suddenly.
Yeah.
Also remember that a large regulated utility or a large regulated private sector company like ExxonMobil is influencing the government
Oh, yeah.
substantially.
Mm-hmm.
A lot of
Closest thing to mortality
effect
we can
both
see in
ways.
this world.
Yep.
Well, so is a company like Apple, right?
Yeah.
So I'm
And
my
or
question is just
Amazon.
more like, is it higher for Exxon than Apple? That's like
No.
I guess that.
those are both such large entities that the probability is essentially zero for all practical purposes. You need to
Well,
look at
for
is
a single one, yes,
size
but
a size 20 company and say
Yeah.
The
There's
better
some-
example now is Sears, which
Yeah.
is sizable but also on the ropes.
But it's
Yeah.
taken like a couple decades for it to kind of wind itself down.
Yeah.
Exactly.
Well, it's actually just changing. It's turned into a holding company, so it's not
Sears
really
as
gone.
we knew it is gone.
Yeah.
Yeah. But
Sort of.
the buggy whip companies are gone too.
And the barrel making companies.
And the barrel making companies, all the Coopers are gone.
Yeah. Actually, a point that Bill just brought up. Do you quantify for gobbling up, such as in Silicon Valley? The personnel is still there. Their products are often still there. The corporate entity known as XYZ Inc. doesn't exist, but that's because all of its products have been consumed by some of the conglomerates.
Right,
Do you look at that?
It's
Or
especially
can you?
easy. This is just a follow-up. It's especially easy in the modern software world, where just to put a wrapper around somebody else's software and call it your own software.
Right,
So-
right.
And so I mean, I guess once again, we're relying here on census, the economic census, and basically the IRS definitions of what it means to be a continuing company.
Okay.
Now, it is the case that in the work that we've done on ages in general, you can ask things like, for example, imagine that if in fact there was a Weibull distribution of ages like we see here, what is the probability of seeing a firm that was 200 years old? Or 250, and are there some in America? And it turns out, yes, there are. There's like the Hartford Current has been around since like 1750 and stuff. Right? And it turns out if you do, so you can look at, for example, things like the order statistics for what is this govern the American industrial establishment. Would you expect to see a firm that started up in 1620 when it's still around? And so you do the calculation, and the answer is yes, there are some farms and taverns in Connecticut that have been around basically for a long time. Right? But that doesn't quite get your question, Kevin. But the basic answer is we do suffer this administrative problem that we have to live with their definition of continuity, which is basically so the Burroughs Adding Machine Company, I believe, has some incarnation post Civil War, but they got bought by DEC in the 1980s, I think, and then DEC got bought by Compaq. And then Compaq got bought by, I forget now, was it Dell or something? I don't know.
Right. What do you
No,
consider
HP.
that
And so-
first incarnation?
And so whenever that happens,
Yeah.
HP,
Yeah,
then,
because-
that's right.
I used that as an example of a merger when teaching undergrads, and they looked at me like, "What's Compaq?" Then I realized, oh wait. you were
And so
all
because
fired.
in that version of administrative kind of like tax collecting, the old Burroughs assets are now filed under the tax return number of the younger company.
Mhm.
It's considered to be a young company, but it's just we're still censored. This is not even going back to the 1976 is right on the cusp of the microcomputer revolution. So presumably you have most of the Silicon Valley firms are inundated with their age. But that's a limitation.
private equity firms trying to buy new firms every year. Like the company that I have been working since 2011 and bought four private equity firms 4 times since 2011. So,
Yeah.
so it's changing hands, those kind of stuff. That's so bad.
Tom?
What's the biological thing that,
Oh, right,
that
right, yeah.
continues to live?
So in terms of that, so we look at this, let's look at the age distribution. So having this with the so age is around 14, but lifetime is around 10, and you look at those. That's very much like insects. And it turns out that early version of theorizing about firms being heterogeneous. This is Alfred Marshall, 1900. Okay, one of the first mathematical early economists. His mental model, his analogy was firms in Britain were like trees in the forest. There were lots of little ones, lots of saplings, but only a few giant ones. That was his mental model.
Mm-hmm.
But it turns out that's actually that's not very accurate for vis-a-vis this, because what you don't see is you would not see Walmart is 1 million times bigger than the modal firm size. Or it's 1 million. So you don't see trees that are 1 million times taller than that. So it's a little. So anyway, so Marshall was right in kind of conceptually, but what all these things suggested is instead of it being kind of once again kind of a well-formed population, it's these what firms look like more like is going to be an animal population where there's simply this kind of spewing out all kinds of potentially fecund matter, right? This stuff that can grow up to be mature, but almost all that mature stuff never reaches maturity. It almost all dies. Or maturity is something that's down here, right? So I think it's so it's at least the case that we found biological populations. We found age and lifetime distributions of insects and other kinds of animals like that. But when you look at things more like trees and things, they don't fit this so well. Yes.
So when we talk about controlling for size, what happens when you control for size by different measures? Because I'm just thinking like Fannie Mae and AT&T are both large in their industry, but in terms
Right.
of number of employees, AT&T's toward its magnitude higher. It's just
Right,
it's
yeah.
inherently more labor intensive.
So yeah, so that's a good point. So typically what you find there is when you look at size in and of itself, you find that right when you the actual position of individual firms in a size distribution depend on how size is defined, but it doesn't change the overall distribution, which is a little bit weird to think about.
Can you say
So
that again?
yeah, so you can measure size by employees or receipts or profitability or a couple other different ways, and you'll always get a power law. You always get one of these very skewed distributions of by market capitalization for the 10,000 public ones. You always get a very skewed distribution. So Microsoft will be high at the end of the market cap one, but modestly down the employee one, 100,000 employees. So a curiosity is that you seem to have this grossly stable distributional form, even though individual firms change the position in it. So it'd be interesting to know if we change my guess is if we change the definition of size, one firm that's here might just go over to here, but I would think you'd get the same shape of these. But this is by employees.
It's funny because I think firm and I think farm, right? Because that's what I deal
fair
in.
enough, yeah.
And I think about like acres and what happens to farms in acreage as they increase. And I think that there's a midpoint where the failure rate is actually higher. So if you're a really small farm, you have better longevity. And if you're a really big industrial farm, you also have really better longevity, but those middle size like acreage, those I think that
Now, could that be
see
due
a lot
to,
of.
is that essentially a consequence of government policy in the sense that the small firms have certain subsidies that are not available to the mid-sized ones?
I mean, the large ones have the subsidies that are not really
Yeah,
so
available
you
to
go
anybody
backwards.
else. But no, I think it has honestly to do with the ability to manage the land
Okay.
and the actual. I'm thinking in acreage or hectares or
Mhm.
whatever. Like the number of employees, the amount of resources you would need to manage a moderate-sized farm. It's probably about as high as it would to operate a large farm, but
Right.
most people
I
are
asked
not
about the
moderate.
regulatory structures because it is well known, right? It is known for the last couple of years. There's a couple of guys down at the IMF here who have done firm size distribution all around the world. And what they show is that when there are very strong regulatory measures in place at certain crisp size boundaries that you basically can break the size distribution. Their example was that in France, if you have more than 5 employees, you have a different set of tax you have to pay. And so there are way too many size 5 firms, and there are way too few size 6, 7, 8, 9. But by the time you get up to 10, it's kind of back on track. Then in France, once you become size 50, EU regulations kick in, and then there's another break in the data. And there's a whole bunch of firms then piled up at age 48, 49, and there's way too few firms at 51, 52.
I
So
wonder if you see the same thing here with the ACA.
you do not see it. So that's,
Interesting.
yeah. So,
Huh.
but it was, by the way, it was predicted that we
Right.
would see it.
Yeah.
And as of right now, we have not seen it.
With
Where
the
you
farm
do see it is the 8A program. Get a lot of 8A firms that are just under the graduation threshold.
This is US firms.
Yes, right, yeah.
The country only goes back to 1635, 1620 or
Right,
something.
yeah.
What does this look like in Europe or Asia or any other market?
So the short answer, Bill, is that only the U.S. has made these data available to researchers so far. But our co-author on this, Eduardo, my co-author is Omar, and Omar has basically been able to get data on Scandinavia recently. So I think that we will be able to do exactly the same kind of thing for Finland for sure, and maybe Denmark or Sweden. So that's kind of coming. I've been told that the data are available for Japan, but that there are 2 separate camps of data. Each camp has half the data, and they're not talking. But we don't. So the short answer is we don't know.
The reason I ask is I thought that there was an arms merchant in Italy that's been in business for 1,500 years.
Right, yeah.
And one of the U.S. car companies named a car after it, and then got sued.
Oh. So when it comes
Because it
to so when it comes to very long life firms, there is a book about this for MBAs called I think it's called The Living Company, and the author is Arie de Geus, who is a Dutch business school professor, and so he does document a bunch of old firms,
Yeah.
and so he says what are the features of the old firms, and just as a footnote, just quickly, the quick kind of 2-sentence version of it is. But he documents old Japanese firms and then a bunch of European firms that are all like they're on over 1,000 years old.
Yeah.
His argument basically is that those firms essentially are all very adaptive. And for example, so like the one I can't remember the name of it, but it's like a Swedish company that started out being a timber company. It then went into mining. Eventually went into like steel. And not the cool thing is it's back to timber now, so it's kind of gone.
Interesting. Like
And then-
3M.
But then, having said that, though, it turns out he actually in his book, which Arie de Geus's book, he actually highlights. I think it's three or four. What's it? 1,000-plus-year-old
Yeah.
Japanese firms. Some of you may have heard this. That's so about 3 or 4 years ago. I have the files on my machine here. 3 or 4 years ago, the Japanese government changed the bankruptcy laws to look more like American and Western laws, and so one of those ancient firms went under.
Ooh.
After in the wake of
That would have been
so-
bad publicity.
Yeah. So, but it is fun to study those oldest firms. And
Yeah.
Thank you, Rob.
thank you. Yeah, thank you.